recovering the image from a degraded image, wherein what we have is basically this output image g of x comma y with us, and we assume that it has undergone some degradation process p. Okay, and the original image, that is the one which we expect to get, that is the one without the degradation, that is our original image f of x comma y. So the output of image restoration is we try to approximate what this f of x comma y would be. Okay, so an approximation of this f of x comma y, it will be the output of image restoration. Now, image restoration is different from image enhancement. Now, image enhancement basically is a term which we use to improve the quality of the image. Okay, so this image enhancement basically is a subjective matter. So one person may feel that one application may have certain steps which is enhancing this particular image for that particular application, which may not suit another application. Okay, so this becomes more of a subjective matter in terms of image enhancement. One thing I remembered with image enhancement, I was supposed to show you all the images of the gradient. Okay, so these are basically the three output images that you will expect from an input image like this. And this will be the output for the Roberts cross operator. This would be for privets, and this is for Sobel. So what I was actually telling you all is, if you focus on this point in the input image, okay, let me just get a magnifier. Okay, so if you focus on this part, the brake lever. Okay, here. So if you focus on the brake lever, you can see that there is a sharp difference between the background, that is this brick wall that is there, which is brightly colored, and this brake lever, which is black in color, okay, or dark pixels. So very low intensity pixels over here and very high intensity pixels in the background. So when you see the output image over here, you'll see that even though the background wall has the same intensity of a single brick. So just consider this particular brick over here and this borders. Okay, the borders of this brick and this particular brake lever. So in your output image, the border is going to be highlighted. Okay, that will be the brightest part of this particular brick. Same thing with this lever. So if I have the same intensity value of a certain group of pixels, and it is having a separate intensity value between a different group of pixels, and these are adjacent, let's say these two groups of pixels are adjacent to each other, then what will happen is the pixels, the two pixels which are forming the edge between these, that is going to be bright in your gradient image. Okay, so that is what it is shown over here. That is the difference between the background, that is this white brick wall, and this brake lever, that is becoming very bright. Same thing in terms of this brake cables that are going through over here, as well as this handle over here, this frame of this bicycle. So all of these are actually very bright, and the only gray levels or very dark ones are the pixels which are having same intensity values as their neighbors. Okay, so that is going to be your output of your gradient image. So it won't necessarily be like a sharp jump from 0 to 255, but across about at least 3 pixels, if you have something like the edge between the objects, about 3 pixel width thick will be your gradient, in which you will have, let's say, 0, 100, 255, 100, and 0. Okay, what I mean is I will not get it over here. I'll have to zoom out just a minute. So if I have, let's say, something like this as my image, wherein I have an object here. So let's say this is black and this is white. So if I just zoom in this part, then 3 pixel width, something like this, wherein this side everything is black, this entire portion is black, and this entire portion is white. In your original image, both in your gradient image, both of this as well as this is going to be black. Okay, and this middle line, that is this edge which was here exactly, that is going to be this middle line here. Okay, this is going to be having the highest gray level, that is 255, because that is like the absolute edge. If you go ahead, it's like calculating the difference between 255 and 0. And here you have 255. Okay, so if you remember the numerical that we had solved, we were basically taking the difference between these two numbers. Okay, so we'll have this central line as 255, and over here you won't have exactly black or white. You will just have a slight different gray level, maybe about 100. Same thing over here, because you would also be calculating the difference between this current pixel and the pixels to its left. Okay, so you won't always get a pixel, sorry, the gradient line or the edge as a single width pixel line. Okay, you may or may not get a slightly thicker one also. Okay, so keep that in mind when you have to calculate the gradient of the image. Okay, so what we need to do in image restoration is try to approximate this original image. Now, along with the degradation process that occurs on the original image, we may also have what we call as additive noise. That is, along with the degradation process in the output image, that is g of x comma y, we may also have added noise into this image. So that is why we represent it with this. That is plus a noise function. That is a two-dimensional noise function because it is in spatial domain. Now, this noise can be either Gaussian noise, that is, you may have the noise spread out something like this across a single pixel in your 2D space, or you may have an impulse noise. So you can have something like having a certain probability. That is, you can have the impulse noise will be given by the probability function, something like this, wherein you can, if it has probability A, then Z is equal to A, probability B, then Z is equal to B, and if probability is 0, if it is not having, if it is having some different value. So if you had like the gray level, basically instead of a certain value which it was supposed to be having, it may have a completely different gray level, say either A or B, depending on this probability value. Now, a special case of this impulse noise is what we call as the salt and pepper noise. The salt and pepper noise, I think we had shown you in terms of that penguin image, if you'll remember, this one. Okay, so salt and pepper noise is basically a special kind of impulse noise wherein the gray levels of this impulse noise is either black or white. So if you have seen the way salt and pepper powder looks, it's basically the salt is white and the pepper powder is black. So that is where if, when you mix both of these together and you spread it, let's say sprinkle it onto a dish, it basically looks at like white and black spots on that particular surface. Okay, so that is where this term for it comes, that is called as the salt and pepper noise, because it has these white and black spots. Okay, so your impulse noise can be salt and pepper noise only if these gray levels, that is A and B, are either black and white. Only two possible values. No other in between values are there in your salt and pepper noise. Now, the image degradation model, depending on this noise, may be slightly changed according to, again, this part that is basically a mess. I'll just redraw this derivation so I can give you all that. But before going to that, let me just give a slide this thing. Now, the image degradation model can be slightly tweaked so that instead of having the noise as additive, we can basically process it independently. So instead of having this, sorry, not g of x plus g of x comma y, we can consider this output as, now this was what the original image degradation model was. What we can also have is this, wherein the noise is added to the image itself after the degradation process, and what we have is the noisy image. So in this particular case, in the second case, what we have to do is we have to process the system itself as considering the noise, and therefore we cannot just ignore the noise. So in this first case, we could just have a separate function to remove that noise and then find the restoration, or do the restoration, image restoration. But in case it is not having this, then we would have to adjust the convolution kernel. That is, because this process P will be, if you remember the equation, we can approximate this first one as a convolution between f of x comma y and some function, degradation function, h of x comma y. That is what gives us this output, g of x comma y. Okay, so in that case, the noise, in the second case, the noise is added to this convolution kernel itself, this convolution operation. Okay, so that is where we have to slightly tweak your convolution kernel. Now, based on this image degradation model, we basically have two ways in which we can, what do you say, that we can restore this image. Okay, so we basically have to, in the first case, that is considered as the unconstrained, constrained conditional restoration. We basically have to take the approximation vector and in turn find out in terms of the derivative of this. Now, this derivation is basically, I will have to explain it. I don't want to do this online because then you won't be having any way in which to tell me the difficulties you all are facing. What we'll do is we'll do this part in the theory lecture, that is the derivation. There are two of these. That is, we basically have this, that is unconstrained, in order to get this our final output, that is this line over here. Okay, and then we have, sorry, this is constrained. Unconstrained, I've written somewhere this part here. So this current thing is a mess. this is not there are steps involved in exactly how to find that out. So I'll do this in your theory offline class. Same thing for constraint, because here we have something called as the Lagrange's multiplier method, wherein we have to again take that the derivative, we have this particular formula, that is this one. Okay, this highlighted one, this line over here. So from this, we are basically getting this equation down, and then at the end, we'll be getting this part. So we will see these two in the next lecture. Sorry, not lecture, Tuesday's lecture. Okay. Regarding inverse filtering, this is pretty straightforward. That is, we are considering this inverse filtering to work with only when we don't have any additive noise. That is, we just ignore this part, and there is a slight change to this, that is with additive noise. So this is pretty straightforward. If you all are not understanding this, I will still cover all of this in class also. Instead of this part, I will cover the inverse filtering topic so that it is much easier also. Uh, in inverse filtering, what we do is we assume that we can get the original image back by just inversing or inverting the degradation process P. Now, we consider the image degradation model, that is, if g of x comma y is some process P on the original image f of x comma y, and we have this additive noise in x comma y. Now, in inverse filtering, we basically, in the first part, we just consider that the noise is ignored. Okay, we assume that there is no noise. In such a case, what we do is we will have to just write this as the what do you say that in the frequency domain, because we basically have this process P as this process P with f of x comma y will be a convolution of f of x comma y with your degradation function. So if I just write this as g of u comma v is equal to h of u comma v multiplied with f of u comma v plus n of u comma v. Okay, so this entire equation itself, we are rewriting it in the frequency domain. Now, in the first case, what we do is if there is no noise, then we have the equation g of u comma v as h of u comma v into f of u comma v. Okay. Now, what we need to do is we just want to reshuffle this equation to find out what is this f of x comma y and what was f of x comma y in this original image. So we can just rewrite this as f of u comma v as g of u comma v divided by h of u comma v. Okay. Now this will only work if h of u comma v is not equal to 0. Now, when we take the inverse Fourier transform of this equation, what we will get is the original image, that is f of x comma y, is basically the inverse Fourier transform of g of u comma v divided by h of u comma v. So this basically is the idea of inverse filtering. Okay, that is, given the output image g of x comma y and knowing what this degradation function would be, we try to calculate what is the original image from this formula. Now, with noise, that is, in case the image has noise in it, did it crash? Great. Open board crashed. And I lost that particular derivation. Okay, anyways, so What we want to do is the second part, which is with the additive noise, that is G of u comma v is equal to h of u comma v with f of u comma v minus n of u comma v. Now we just want to reshuffle this so that we find out what is f of u comma v. So we take n of u comma v to the left. So we would have g of u comma v plus n of u comma v is equal to h of u comma v into f of u comma v. Okay, just reshuffling this equation and then finding out what is f of u comma v. So this would be g of u comma v divided by h of u comma v plus n of u comma v divided by h of u comma v. And finally, f of x comma y is equal to inverse Fourier transform of g of u comma v divided by h of u comma v plus n of u comma v divided by h of u comma v. Now, the problem with this is with inverse Fourier, not inverse Fourier transform, with inverse filtering is if this noise is very strong, then it becomes a very big problem to approximate this image. Okay. Now, there were tests done on using inverse filtering to find out to remove the degradation process basically, and they came to the conclusion that this inverse filtering works best when there is no added noise in this. So in this particular case, that is with the added noise, it does not work properly. Okay, so that is the reason why we just consider sorry, I wrote this equation as a mistake. Did a small thing. This should be negative here. Just realized it now that I wrote the first equation as positive, as negative. That is why I was getting this as positive here. Okay. So they realized that when there is added noise in the image, then inverse filtering does not work very well. So what they did was they came up with another method which was called as the Wiener filtering, which is used when you have much more noise in the image and which cannot be removed using inverse filtering. Let's just check. Okay, I don't have the image also. You can just go. Okay, I'll add the images regarding the error removal part with Wiener filtering and with inverse filtering. Okay. Now, in Wiener filtering, what we do is we try to approximate instead of actually finding out what is f of x comma y. We take an approximation of this image, that is f cap of x comma y. Here, this part. Okay, so this f cap is basically an approximation of what the original image would be. We don't try to find out what the original image is, we just try to get an approximation of this original image, and we try to reduce the difference between the f cap, that is the approximation, from the original image. Now, the way we can reduce this is by having what we have as the mean square error, which is basically given by the square root of the difference. Mean square is calculated by square root of the squares, square root of the sum of squares, basically, the difference of squares, not sum of squares, difference of squares. That is how you find out the mean square error. What we want to do in Wiener filtering is we want to minimize this mean square error in terms of the approximated image with the original image. So when this mean square error of this is minimum, we can say that our approximation of this image is very close to the original image. So that is why what we do is we take this equation, which is how we calculate the mean square error, and we put this equation in here. Okay, so we basically, how did that switch to the laser pointer? Does the laser pointer? Okay. Yeah, I'm having a bit of a problem in terms of this. Are you all seeing the red dot or the cursor? No, you all are seeing the cursor. I don't know why it is showing. Okay, yeah. So what we want to do is we want to approximate this image. So what we do is we substitute it in the equation and we try to find out what is going to be this f cap of this. So because it is a convolution, over here, we shift it into the frequency domain and then we get this equation wherein instead of h, we are basically having the equation m, which is a slight modification of the original h function. Okay, so from this we get m function approximation, which is muv into guv, and muv is basically given by the equation h cap. It's not h cap, it's there's a term for it, conjugate. H cap, h asterisk, this function is basically the conjugate function of h. And conjugate is basically if I have, let's say, a minus b, then the conjugate of this would be a plus b. So if it is normally used in terms of complex numbers, why is this point not coming? Okay, so it is usually used in with complex numbers. So if I have a plus ib as my complex number, its conjugate complex would basically be a minus ib. Okay, so that is what is used over here. So if you have the equation of h of u comma v, in m of u, mu comma v, we are basically using the conjugate of it, and we are dividing it by the square of this, that is going to give us the magnitude, and this ratio is basically what we call as the power spectra of the noisy image. So this is going to give us the final output, and the problem with Wiener filtering is we cannot get a very good approximation of this power spectra. Okay, this P of n comma u comma v, that is very difficult to accurately identify, and therefore even though Wiener filtering is said to work with very much better than inverse filtering in case of noisy images, the problem lies in accurately estimating this, okay, this ratio. So what we do is we usually consider the numerator of this equation as 0, and in such a case we then have a special case wherein MUV is same as 1 upon HUV, and therefore in that case your Wiener filtering becomes the same as inverse filtering, and you would have the equation as this part. Okay, so you would be having this as your final output. So you would be getting your equation, this conjugate would be the same. You would basically divide this by square of this. So you would actually get the output as MUV as 1 upon HUV, which you substitute in this equation. That is the same as inverse filtering. Okay. So that is like a special case wherein there is no noise at all in your input image. Now, the next part is your geometric rectification. That is, in case your image has any kind of geometric errors, then how exactly do we find out that geometric errors? Okay, so the most common case of geometric errors, okay, I think I'd shown you all some images. Yeah, this one. So this is especially the case with wide angle lenses, as I think last time one of you all had told, the term used for this is fish eye, okay, or the fish eye effect, wherein the straight lines, which are supposed to be straight, especially at the corners of that image, will come as curves instead of a straight line. They will be seen as curves. So this we are trying to remove. This is just one example of geometric errors. We basically have another issues wherein if you see these two images, this part is common with this image. Okay, this part over here is common with this, but we don't have this portion. So if you see more closely, this is basically both of these are satellite images, and in case of satellite images, what happens is as the satellite moves, the Earth has also rotated. Okay, so in such a case, we may not get an accurate image of the entire area as a flat surface. What we get is a slightly shifted version, wherein you would get something like this. Okay, what is that? Okay, I haven't exactly put that image here. Okay, so what we want to do is we want to find out in this particular image, if we want to remove the geometric errors. This is just one example. Now we have some more that is called as, if I have something like a grid as my original image, let's say something like this. Okay, a proper grid, then you may get this as something like this, wherein certain parts of the image are much closer to the camera compared to the others. I think you all must have come across this last year when you all were sending images of the answer sheets. If it was not, if your question, if your answer sheet or the paper was on a flat surface on a table, let's say, but when you were clicking the picture, when your phone was not exactly straight or parallel to the surface, so you would get something like this. That is, the top parts of the image would come smaller compared to the lower parts, or the other way around. So you would basically have what we call as the perspective distortion, wherein objects further away are perceived as much smaller compared to objects closer to us. Okay, that is why we consider this as whichever part of that image is further away, that is seen as much smaller compared to the part which is closer. Okay, another geometric distortion is pincushion, in which we basically are having something like this, wherein parts of the image something somewhat uh, squished together. So we will get something like this. Okay, this is called as the pincushion effect, or the pincushion distortion. And the last one, which is now these are given in your textbook. There may be more distortions also. Is barrel distortion. So something like this. Okay, so the main thing what we do in removing geometric errors or any of these types is we basically have to find out certain points in that particular image and map it with our output image. Okay, that is, in this particular image, let's say we want to find out where this point lies, that is some common points in the original image, and let's say over here it is this point. Okay, let's just assume that it is. So what we want to do is we want to find out where these points are lying, and then we want to confirm that the pixel intensities at this intersection is actually the same. Okay, so removing of geometric errors is basically a two-stage process. That is, once we know what these two common points are between the original image and the distorted image, we use these points as reference points to find out what was the geometric distortion applied. We basically get an equation which is we assume is some kind of combination of scaling. In your computer graphics, you all must have come across these transformations. That is image transformation. That is scaling, rotation, shear, and some more of them were there, if you all remember. Okay, so what we consider is this output image, that is what we currently have, is undergone a combination of all of these processes, and we want to find out one single matrix, one single operation which can approximate all of these operations in one single matrix. Okay, so what we do is we consider that the image has undergone some transformation as a combination, and therefore we consider this as an affine transformation. Now, what we want to do is we want to find out what is the equation for this affine transformation, and to do that we need to identify a reference points in our images. So if you see this bottom left image over here, in these you have these numbers marked. So these numbers are basically what we are having points in our images which can be identified between this image on the left, that is our original source image, and we assume that this is our latest image, that is on the right, and there are certain changes. Now, unless you are into information gathering, that is in terms of the national security level, that kind of thing, you won't be scanning a certain area every day. Okay, or even most of the times if you are getting satellite images, they are going at consumer level, these are going to be about at least a difference of a few months minimum. Okay, uh, most of the times you will find these surveys done maybe once in 10 years, especially for recently there was that problem of that Goa coastal zone management plan. So that usually comes under what we call as the regional plan. So they have this regional plan every 10 years, and the way they assign certain zones is by looking at the satellite imagery of the latest place of that particular area, the latest satellite imagery. They compare it with the previous one, which was usually 10 years back, and then they find out if there was any differences in that. Now, there are also researchers in terms of finding out the loss of the forest area in terms of the size of lakes. A lot of research has been going on in terms of finding out information from satellite images. Okay, now the major thing what we want to do is with satellite images, because of the rotation of the earth while the satellite is moving, that is, if you see this particular thing, this I think is an approximation of a geostationary satellite, which is stays in the relatively same location. I think I was giving examples of this, and this is what I'm talking about in terms of a low Earth orbit satellites. Now, these will usually travel across the other plane of rotation of the Earth, that is from north to south. And because of the rotation of the Earth, it is not going to get the same image in terms of the output. If I just set the scanner to this, what will happen is if I get a certain location, let's say this one, by the time the satellite has moved to the next block, the expected image will not be over here. It might come as this point over here. Okay, so this shift has to be adjusted. Okay, and especially in terms of low Earth orbit satellites. That is what we are doing over here. That is what we are trying to find out exactly how this particular image on the left, which was the older image, and this newer image, how exactly these are aligning. Okay, so any new information that will come in this, that is what we want. So to align this particular image with our old image, we first have to find out what are certain identifiable points in both these images. Okay, so what we do is we find out these reference points. So usually for finding out reference points, we consider certain uh, shapes which will not change over time, certain landmarks in these images which will not change. And these landmarks also, we have to keep in mind that these landmarks are easily identifiable. For example, if you see 1, 2, 3, and 4 over here, these landmarks are easily identifiable. System just restarted. I don't know why. Just give me a minute. It's surprising that I am still seeing the presentation. Students, can you all see the presentation? The screen is shared. Okay, okay, just a minute. I'll just share it again. I don't know why, but my laptop suddenly restarted. Okay, sorry. Uh, what we want to do is in our image, we want to find out the points in our image which are easily identifiable. Okay, so if we want to map both of these images without the distortion, we want to find out points which can be easily identifiable in both of these images. So the most common points what we can see over here will be based on certain landmarks, something which will not change across time and which can be easily identifiable. So if you have a look at this particular building, it has this H kind of shape for its roof. The same building can be seen over here. Okay, so if I just zoom out from this, you can see that this building here is the same as this building here. Only thing, this image is slightly rotated. Okay, this particular image on the right is slightly rotated compared to this, and we want to remove this rotation. Okay, so what we want to do is the corners of these buildings, this particular building, the four corners, we can consider that as 4 points. Okay, so we consider the 4 points of this particular building, 1, 2, 3, 4, as our reference points in the old image as well as the new image. Along with that, we also consider additional points. Okay, especially if you see this particular road over here, the point at which the road splits into two. Same thing over here, here, and here. Okay, so these points can be identified and therefore marked in both of these images. So in my output image, all these 10 points which are over here in this particular image on the bottom left. Okay, so all the 10 points in this bottom left image have to align with all the 10 points in my bottom right image. Okay, so this way in which you can identify, after all these points are identified, what we want to do is we want to find out what would be the possible transformations to be applied so that all these 10 points are mapping together. Okay, if after applying this transformation to my this old image, how exactly I will be able to plot all these 10 points into my new image. Okay, so this equation we can find out based on the values, the coordinates basically of our all these 10 points. Now, depending on the number of points that I have, the number of reference points that I have, I will get a slightly more complex equation which will approximate this affine transform much better compared to my equation with less number of points. Okay, so what we need to do is we basically will need, just give me a minute because this requires the equation. We are basically approximating that the original image undergoes an operation phi1 and phi2 such that x of the image will produce an equation a1 plus a2u plus a3v plus a4u square plus a5uv plus a6v square. Same thing for y. Sorry, not a1, this will be b1, b2u plus b3v plus b4u square plus b5ub plus b6v square. So what we need to do is, based on these points, we find out what are the minimum number of points that we will need. So what we do is, based on all of these reference points, we substitute the coordinates of these reference points into this particular equation and find out what each of these A1, A2 up till A6 and B1, B2 up till B6. So once we get these equations, that is the coefficient values, we can then get the final output as x1, x2 up till x6, sorry, multiplied with the coefficients A1, derivation, the two of those are there. So after that, we'll see about this. Okay. Any questions you all have with this image restoration? Okay. In that case, that's it for today. You all can leave. Thank you.